Welcome. Have you ever wondered if we could build a computer that physically operates like the human brain? That is the exact goal of neuromorphic computing. It's a branch of computer engineering that designs hardware and software to mimic the physical structure and functional principles of the human brain and nervous system. To understand why this is revolutionary, we need to look at traditional computers. They rely on something called the von Neumann architecture, which separates the processor or CPU from the memory or RAM. To perform any task, data has to constantly travel back and forth between the two. This constant data shuffling creates a traffic jam known as the von Neumann bottleneck. It severely limits processing speed and consumes a massive amount of energy. Neuromorphic computing abandons this traditional design entirely, looking to biology for a vastly more efficient blueprint. So, how does it actually work? To replicate the brain's efficiency, neuromorphic chips use physical architectures that resemble biological neural networks. There are four core principles. First, artificial neurons and synapses. Instead of traditional binary logic gates, these chips are built with electronic equivalents of neurons, which are the processing units, and synapses, which handle memory and connections. Second, co-located memory and processing. In the human brain, synapses handle the storage and the processing of information simultaneously. Neuromorphic chips replicate this by weaving memory and processing together locally on the chip, completely eliminating that data bottleneck we talked about earlier. Third, spiking neural networks, or SNNs. Traditional processors run on a continuous rigid clock, consuming power constantly. Neuromorphic chips are event-driven. An artificial neuron only fires, or spikes, data to the next neuron when it receives enough electrical stimuli. If a part of the network isn't needed, it stays dormant, drawing virtually zero power. And fourth, massive parallelism. The brain doesn't process data sequentially. It processes millions of sensory inputs at once. Neuromorphic systems operate entirely in parallel, making them exceptional at handling complex, dynamic, real-world data in real time. This technology is rapidly moving out of the lab and into practical applications. Let's look at three prominent examples. Number one, Intel's Loihi. This is a cutting-edge research chip that packs up to 1 million artificial neurons. Researchers actually used Loihi to build an artificial olfactory, or smell system, because its architecture mimics how the brain adapts as it learns. The chip learned to instantly recognize the chemical signatures of 10 different hazardous materials from just a single training sample. And it did this consuming thousands of times less energy than a traditional AI model. Number two, IBM TrueNorth. Developed under DARPA's Synapse project, this chip excels at complex real-time visual pattern recognition. It can process live video feeds to independently identify and track cars, people, and bicycles. The standout feature? It performs these complex AI vision tasks using only about 70 milliwatts of power, roughly the equivalent of a standard hearing aid. Number three, event-based cameras. Traditional cameras capture massive amounts of redundant data, like stationary backgrounds, which wastes memory. Each pixel acts independently and only fires a signal if it detects movement or a change in brightness. This allows robots to track incredibly high-speed objects in real time with virtually no motion blur and drastically less processing power. Ultimately, neuromorphic computing solves the massive power consumption problem of modern artificial intelligence. While traditional AI requires giant, power-hungry data centers to learn, neuromorphic chips will allow edge devices like autonomous drones, smart prosthetics, and remote sensors to process complex AI tasks and learn continuously on their own, all while running on a standard battery. For full content, visit www.vlrtrain.com. Please subscribe and share for more videos.